Alright, calculus, these videos are late. It's 7 at night. Had to get some other work done. But just to review these horror of things like a railroad track, railroad, train kind of thing. What else moves horizontal? Some game. Last mentioned like the carnival game. Carnival games where you shoot stuff down. It's like these little targets and they're moving horizontally. Vertical, there's a pretty common one that we use a lot. It's the elevator. I can't even write here. There we go. The elevator. But you know, a lot of times when we look at something that just moves up or down, particularly up, we talk a lot of times about rockets. You know, as they leave the planet, kind of thing, and measuring their movement and stuff. Because that's the general idea. We're looking at movement, but we're really only interested in horizontal or vertical only, not curving, but just up and down or just left and right. Okay, so let's look at this first one. It says, show its position on the number line for t equals 1, 2, 3, 4, and we got this equation. And what it's saying right now, well, we have this horizontal line. It's a left and right line. So we have these dots here. I'm going to have these dots. And if I were to plug in these numbers, 0, 1, 2, 3, 4, where would I be? Well, if I plug in 0, I'd be at -3 right here. So there I am at t equals 0. And then if I plug in 1, that's going to be 1 squared minus 2 minus 3. That would be -4. So here I'm at 0, then I'm at -4, and then go figure, I plug in 2, now I'm back at -3. So I started at 0, 1, 2. And when I plug in 3, I actually get 0. So in other words, S of 3, so S of 0 equals -3. S of 1 equals -4. S of 2 equals -3. S of, what are we at? 3 equals 0. And then if we plug in 4 into that equation, you would get 5. So if we're counting this out loud, you know, we're starting here at -3, then we go 0, 1, 2, 3, and 4. So it's a moving line, and it's kind of weird to plot it just horizontally because you got overlap. It's like we move left, and then we move right over the same distance that we move left. So this horizontal movement or this vertical type movement on the number line is kind of curious. It's a different type of measuring than we're used to. We're used to two axes of movement, you know, a horizontal axis and a vertical axis. But in order to really look at this analysis of movement, we want to start out simple. Only left and right or only up and down. Well, let's jump into it. Velocity right here, it's how the position changes over time. And when we're changing over time, that's really a rate. And so velocity, the big idea is that velocity is the derivative of your position, which starts out as s prime t. Now, this is a lot of complex stuff here, but I like to think of all this in a picture because we know the good old x and y axis. We know to the right is positive, to the left is negative, up is positive, down is negative. So this is kind of like a guideline for looking at velocity. If you're looking at velocity vertically, just remember up is positive and down is negative. Similarly, right is positive and left is negative. So, you know, those are big things to remember. Up and right are positive directions, left and down are negative directions. But then here's a huge thing. If your velocity equals 0, you are not moving. And when you're not moving, we actually have a word for that in the English language. We call it stopped. Okay. Now, there's one other measurement to really consider when you're looking at velocity, and it's really the same thing, but just a simplified version. Because when we say velocity to the common person, they think speed. And velocity can be negative, but speed can't, because speed is purely how fast you're going. It doesn't care. Who cares? Who really cares which way? I don't. And speed sure doesn't. But when we talk about speed, with speed, it doesn't really matter what direction you're talking about. Speed is just speed. It's how fast, not which way. So, how fast, not which way. Not that. Just how fast. Okay, so let's look at some more examples here, or some notes that we're looking at. And now acceleration. Acceleration. If I can spell this. Oh, it's just one L. Acceleration. There we go. And so acceleration, or A of t, as you know, is the shorthand for it. That's the derivative, with respect to time, of course, of v of t. So one way to think of it is kind of this big thing here. So A of t is the derivative of velocity, which was the derivative of position. So it's like the second derivative of position. So on your cars, you have two things that actually change velocity. And acceleration is kind of like a push or a force making change. It makes stuff, not just stuff. It makes velocity change. So how do you change the speed and direction, I guess you could call, on your car? Now this is kind of weird because we're talking about direction, but really just forwards or backwards. And the things that do that are your accelerator. Ooh, that's interesting. Is there a reason those are the same word? No. Yes, it's not a coincidence. They are the same word because accelerator changes your velocity. That's why it's called an accelerator. And the decelerator, but for the most part, we have a shorter word for that. Brake. I like decelerator better, but brake works just fine. Okay, so acceleration positive. So we still have this same thing where we're talking about positive, negative, positive, negative. What you want to be really keeping in mind, though, is that accelerating means it kind of being pushed. So your push to the right, or your push up, or your push left, or push downwards. And then when there's no push, it's more like you're coasting. You're not pushing, you're just kind of free riding. Well, let's start analyzing some of this a little bit more in depth, even with just those pieces. It means, so when we look at here, the acceleration is 0. Doesn't mean that you're stopped, because you can coast. In fact, sometimes we call it cruising. And there's a specific thing we have in a car where the acceleration equals 0, and it just kind of maintains that constant velocity. It's called cruise control, at least in the American language, the English language, we usually call it. I don't know if they have something like that over in England, but yeah, we call it cruise control here in America. Also, just because you have positive acceleration does not mean you are moving to the right. Okay, so for example, let's say that I'm here. Okay, let's make a happy face here. So here's our happy face. Boom. And this happy face is encountering some wind. So here's the wind. And it's going against us. So if we're thinking, kind of like an arrow. Do I have an arrow up here? I thought I did. Yes, I do. Well, so here's the wind. It's blowing against us. It's pushing against us. But I'm walking this way. So my velocity, if you were to think about this, my velocity is to the right, so velocity is greater than 0. But my push, my acceleration, with all these pieces here, is not. My acceleration is left. Velocity is right. My acceleration is left, it's negative. Now this is an interesting thing. When you have opposing forces right here, some stuff cancels out. You know, I might be slowed down or actually pushed back against my velocity. So there's some cancel out action. Some speed, I guess you could say, is canceled out. Some, not all necessarily, maybe all. But so what would that do to your velocity? It would decrease it if we were opposing directions. So it's decrease it. Now, how do we say that in the English language? We call that going slower. It's going slower. All right, so let's look at this one. Now we got a new function here, and we're going to find the velocity function, the acceleration function. We're going to do all this huge analysis, and then we're going to start to describe it in words. Just a little note, this absolute value piece here, this is the speed, just so you know. And we're going to use all this information and analyze it, just to analyze the movement of the particle. So let's start out with velocity. Velocity is the derivative of position, because it's the measure of the rate of change of position. So that's going to give us, if I were to put the derivative here, 2t minus 4. Then I take the derivative again to get acceleration. The derivative of 2t minus 4 is just going to be 2. So now we're looking at how to interpret all these things. Let's go and start with the easy stuff. A of t equals 2. There's no variable in there, so no matter what I plug in, it's always 2. So I'm just going to fill in 2 all the way down on that column. And that's kind of an interesting thing. It's always pushing right. It's got to push right, or push to the right, always. Because it's always 2. It's never 0, it's never negative, it's always pushing right. Okay, so S of t, that means we plug in these values. We plug in 0 into the position function, we get 2. If we plug in 1, that's going to be 1 squared minus 4 plus 2. And that's going to be 1 plus 2 minus 4, that's negative 1. Okay, not too bad. When we plug in 2, so that's 2 squared minus 4 times 2, so 2 squared is 4. Minus 4 times 2 is 8, so 4 minus 8 is negative 4, plus 2, that's negative 2. And then these other pieces are going to be negative 1, and 2, and then 7. You can check me on those calculations, but they're pretty easy to figure out. Okay, so now we're going to plug in the values into this linear function that represents our velocity right here. So if I plug in 0, I start at negative 4. And that's just a simple slope of 1 in the x direction, 2 in the y direction. So I plug in 1, that'd be 2, minus 4, that's going to be negative 2. And then we got 0, 2, 4, and 6. Yeah, it's a linear function, pattern of up 1 in the x direction and up 2 in the y direction. Now the speed is just the absolute values of those. So we start out at 4, then 2, then 0, then 2, then 4, then 6. And notice here, on our way to 0 for our speed is decreasing. So we're slowing down in those first 3 parts, and then the last 3 parts we're speeding up. That's actually going to make a little more sense too when we look at our acceleration versus our velocity. Okay, so describe the particle's motion. So in the first part at 0, just the motion, not where are we, but which way are we going. The negative 4 velocity means that we're moving left. But the push, our acceleration, our a of t, is always right. And because these are opposing, we're moving left but being pushed right, we are slowing down. Well, let's look at the next one. We are still moving left, still pushing right, and again, opposing forces, we're going to slow down. Move a little slower. Now our velocity hits 0. V of t equals 0, right here. So V of t equals 0 means that we are stopped. And this is an interesting interpretation. If you're stopped, are you speeding up or slowing down? It's kind of different on each side, so it's hard to measure that. So you just say stopped. You're not really speeding up because I guess you're about to speed up, but you're not actually speeding up yet. At 3, we are definitely, now we're going to be moving to the right because our velocity is positive right here. This is a positive 2. And we're being pushed to the right as well, so that's making us go even more right, which means we're going to go faster. We're speeding up. And the same thing happens for these last two pieces. Velocity is positive, acceleration is positive, therefore we're moving faster. Velocity is positive, acceleration is positive, therefore we're moving faster. So what's kind of the general idea here? If our velocity and acceleration match, if they're both the same, we move faster. But if they are opposing, one's left, one's right, or vice versa, then we're slowing down. So that's the general idea. Now if I were to take a little circle here, let's go ahead and create a circle just for ourselves. We'll put it, where do we start at? We start at 2. So we're going to start here. And we're trying to figure out, okay, where does this piece move? Where does this thing go? It starts at 2, then it goes to -1, then -2, and then back to 1, then 2, then 7. And so it's going here and it's slowing down and then it's speeding up. Whoops. Looks like I missed clicking on that piece there. Let's undo that. Undo it again. Okay, so we start at 2, and then we're going down to -1, slowing down, and speeding up way up there. I'm faster than the circle. Alright, so let's look at the next example here. Now we're going to get really into this kind of how do we look at these opposing forces. If we know that A of t is greater than 0, so this is positive, A of t less than 0 is negative, A of t equals 0 is 0. Okay. Then V of t, that's positive, then we got negative, and then 0. So this is a stopped, and this is moving left, this is moving right. So let's look at what happens. This is a push right and a push left and no push, the coast. So we're moving right, we're being pushed right, we are going faster. We are pushing left, but moving right, that means we are going slower. It's slowing us down because it's opposing forces. One's going one way, the other one's going the other. If the acceleration is 0, in other words, there's no push, but we're moving right, it's just a constant speed, or constant velocity to the right. Okay, now let's look at when we're negative left movement. So we're moving left, we're going to the left, we're moving left, but we're being pushed to the right, opposing forces, which means we're going slower. Similarly, moving left, well, not really similar, it's actually the exact opposite. Moving left, pushing left, we're moving left no matter what, but we are going faster because the push is going with us, it's helping us. Okay, so now we're constant again because there's no push. Constant velocity to the left. Now when you're stopped, again, it's kind of that in-between thing. It's like you're not speeding up, you're slowing down, you're actually stopped, which is what happens in between those two things. So we're just stopped. Again here, we're just stopped. We're about to go to the right. We're about to go to the right when we're being pushed right. And we're about to go to the left when we're being pushed left. But when there's no push and we're stopped, we're just completely stopped. You're like concrete, not moving at all. Stationary, with no plans to move. So interesting stuff happening there. Let's try and put this to an analysis here. We're going to look at a couple of examples. How many are we going through? I think just example 3 and 4. Yeah, we're just going to look at 3 and 4, then we'll jump into the second part of the video after that. Okay, so first we have a position function here. A particle is moving along a horizontal line at this position. Do an analysis of the particle's direction, right or left, acceleration, which means pushed, left or right, and the motion, which means speeding up or slowing down. We're just going to say faster or slower. In fact, we'll probably just say F or S. And then the position. Now the position is kind of like a overkill, because once you know the important stuff about the movement, you can answer the most important questions about position, but you don't really need to do much more than that. Okay, so let's start with velocity. Velocity again, step one. Velocity, remember S prime of t, so take the derivative equals v of t. The derivative of t squared minus 6t plus 5 is 2t minus 6. So when does velocity equal 0? So if I were to solve this equation for 0, that means that t would equal 3. Because if I plug in 3, v of t equals 0. So let's make a number line. V of t, showing when the object is stopped and the sign and direction of the object at times left and right of that. Okay, so first, at t is greater than 0. So we're starting at 0 here. Let's just, check at like 1, 2, 3, 4. Let's start with that at 1, 2, 3, and 4. So at v of 1, I plug in 1. That's going to be 2 times 1 minus 6. That's going to be a negative. That means that I'm moving to the left because it's negative. And at 2, if I plug in 2, it's still negative, so I'm still moving to the left. But then at 3, that's when I hit my 0. So I'm stopped. Now at 4, I'm actually changing direction, because 2 times 4, if I plug that in, is 8. Then subtract the 6, that's 2. That's a positive number. And a positive velocity means movement to the right. Now let's look at acceleration. So we kind of got a start on velocity, but let's look at acceleration. A of t equals 2. Now this is pretty similar to the last one we looked at. It was a constant acceleration, not much change in it. And that'll change in the next example, but for now we're just looking at the constant acceleration. Does acceleration equal 0? No. Why? Because it's a constant. It doesn't change. It's 2. A of t equals 2. Always. So, what is it at t equals 1? What is it at t equals 2? What is it at t equals 3? What is it at t equals 4? It's always pushing to the right. Remember, this is a push. It's not actually a movement. It's just a push. We're constantly pushing to the right. It's always positive, 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 positive. The motion then, let's describe the motion at 1, at 2, at 3, at 4. Okay, so now we're talking about slower, faster. Is it slowing down? Is it speeding up? Are the forces opposing each other, or are they going with each other? Which is it? At 1, we have movement to the left because velocity is negative, pushing to the right because acceleration is positive. So we have left versus right, opposing forces. That means let's call S for slower, slow down, and F as in faster for speed up. Alright, sorry about that interruption. I had something pop up here for a second. So F, we were saying, is faster, or to speed up faster. So looking at these pieces, let's see what's happening at 0. We didn't even check 0. Well, it says assume that's greater than 0. It said that somewhere. Oh, right here. T is greater than 0. Okay, so if I'm looking at t is greater than 0, I'm not really caring about 0. But what's happening here? We're pushing to the right, moving to the left. That means we are going slower because we have opposing forces. And next we have pushing to the right. Again, we have opposing forces. Opposing forces means we're going slower. Now when we're stopped, it's kind of like that, well, neither. Because we got movement equal to 0. We're not moving. but we do have a push, but we're not moving, so we're not really speeding up. We're just kind of in between. And then at 4, we double up. We got movement to the right, acceleration to the right, then we start speeding up. Now the position, I'm actually going to skip this just for this sake. But I'm really, when you guys do this analysis, especially on the quiz, I really want you to look at these 3 pieces. That's what I'm most concerned with. The other things that we're going to talk about, higher level questions and how to answer those, dealing with the other pieces. All right, let's look at example 4 and wrap up this video. A particle is moving along a horizontal line with this position function. Do an analysis. Okay, so now it's not giving all the prompts. We got to kind of consider what we need to really measure. But what I'm trying to look at now is find the velocity and acceleration. So we have the different pieces here. Let's find velocity. That's s prime of t, by the way, equals the velocity, which in this case, the derivative is going to be 3t squared minus 18t plus 24. And then acceleration is going to be s double prime of t, which is the derivative again. Now we have 6t minus 18. So let's look at these pieces. We're going to look at, let's say, 1. Let's go all the way out to 5. Let's go crazy. 1, 2, 3, 4, and 5. Okay, so I'm looking at this function, and man, that looks kind of hard and crazy to do. But I'm going to factor it just for a little bit easier calculation. So if I factor out the 3, then I can also factor this left over. I'd have t squared minus 6t plus 8. So that's going to be t minus 2 and t minus 4. All right, so let's plug in 0. We plug in 0, we get 24. So that's positive, which means we're moving to the right. We plug in 1, that means I get a negative here times a negative there. That's still positive. I'm still moving to the right. Now when I plug in 2, I get a 0. That first factor turns to a 0. So I'm going to get a 0. So I'm not moving. I'm stopped. And then when I plug in 3, I get a positive for the first term, but a negative for the second term. So that's actually a negative there. And that means we're moving to the left now. And when I'm at 4, again, I'm at 0. So I'm stopped once again. And then I look at 5. I'm going to have positive times positive. That's going to be a positive overall, which now I'm moving back to the right. This is crazy. It's like we move left, then we move right, then we move left, and right, back and forth. So let's do the same thing, but look at the accelerations. These are the pushes. Remember, this is the push. 1, 2, 3, 4, 5. So at 0, you plug in 0, we got a negative. So we're pushing to the left. And at 1, let's see, again we're negative, so we're still pushing to the left. And at 2, we're at 0, so we don't really need to measure the push, but just for fun, we plug it in. We get negative, and we're still pushing to the left. At 3, now this is interesting. 3, we get 0. So there's no push. It's just a coast. And then at 4, now we're back to the positives. Here at 4, that's positive. So that's going to be pushing to the right. And then at 5, again, we're positive. At 5, we're positive again, and we're pushing to the right. So we got left, 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 no push, right, right. So let's look at the motion. At 0, we are opposing. So this is moving slower because we got opposing forces. At 1, we are moving slower because we have opposing forces. And at 2, what's happening? We're moving left, but we're constant. So, no, what are we doing? No, we're stopped. We're stopped. No movement. So we just keep on moving. Let's look at 3. What's happening? We're moving to the left, but our acceleration was 0. So this is not it's not changing faster or slower, it's constant. Then at 4, we have movement to the right, but again we're 0, again we're stopped. So nothing there. Then we look at 5, we are moving to the right and we are pushing to the right. So this is where we start to speed up and get a little bit faster. Again, the position, not as worried about right now. We're going to get more into that. But here's kind of like the critical things. Critical as in the important. Note that the position graph is not like the other 3 graphs. Okay, we're not really looking at it, but we're really focusing on the other 3. What we're looking at is the critical times of movement is when v of t equals 0 or a of t equals 0. When is velocity 0? When is acceleration 0? Because that's where all the information is at. Okay, so this is the end of part 1. We're going to start part 2 to wrap this up when we get into vertical motion. But this was horizontal. Tune in to part 2.